Have you ever noticed that when you put a straw in a glass of water, it looks bent? Well, that's not your eyes playing tricks on you. It's a real physical phenomenon called refraction. Today, we're going to peek behind the curtain and see exactly how this science of bending light makes everything from glasses to giant telescopes work. Let's get into it. So here's our game plan. We'll start with what refraction even is. Then we'll cover the rules that make it all happen. After that, we'll dive into the two main types of lenses, converging and diverging, and finish it all off with a side-by-side comparison. All right, first things first. What in the world is this light-bending magic we call refraction? I'm sure you've seen this a million times, right? You take a perfectly straight straw, pop it in a glass of water, and suddenly, right where it hits the water, it looks like it's broken. This isn't an illusion. It's the perfect real-world example of what we're talking about today. That's refraction, right there in your kitchen. Okay, so here's the official definition. Refraction is just what happens when light passes from one material or medium, like air, into another one, like water or glass. As the light crosses that border, it changes direction. It actually bends. And the reason is that light travels at different speeds in different materials. Kind of wild, right? Now, this bending isn't just random, not at all. It's incredibly precise, and it follows two fundamental laws of physics. You can think of these as the rules of the game for how light behaves. The first law is pretty simple. It just says that the light coming in, the light that gets bent, and a line drawn straight through the surface all stay on the same flat plane. Easy enough. But the second law, well, that's the powerful one. It's a mathematical rule that lets us perfectly predict how much the light will bend for any two materials. It's like having a consistent recipe. And that predictability is what lets us engineer lenses so precisely. And because we have that perfect recipe, we can shape glass to control light in amazing ways. This brings us to our first type of lens, the convex or converging lens. And like its name says, its whole job is to take scattered light and bring it all together. Let's start with the simplest case. Think about light from something super far away, like the sun. Those light rays are all coming in parallel. As you can see in this diagram, the convex lens grabs those rays and bends them so they all meet at one single sharp spot. We call that the focal point. The image it creates there is tiny, upside down, and what scientists call a real image, meaning you could literally project it onto a screen. Okay, now watch what happens when we bring the object closer, just beyond a point we call 2F. If you follow the light rays here, you'll see the image now forms farther away from the lens. It's still real, it's still inverted, but it's gotten a little bit bigger. You're starting to see the pattern, right? The closer the object gets, the farther away and the bigger the image becomes. And right here, this is the sweet spot. If you place the object at exactly that 2F mark, look what happens. The image forms at the exact same distance on the other side, and it's the exact same size as the object. It's this perfect, beautiful symmetry. And this isn't just a textbook diagram. This principle is actually used in things like photocopiers to make a perfect one-to-one copy. But hold on, because when we move the object inside the focal point, the rules completely change. The light rays still bend, but now they spread out so much they'll never meet. Our brain, though, it's clever. It traces those rays backward to an imaginary point. This creates what we call a virtual image, one you can't project, that appears way bigger and right side up. And if that sounds familiar, it's because this is exactly how a magnifying glass works. Okay, time to switch gears. Let's look at the other side of the coin, the concave or diverging lens. If a convex lens is all about bringing light together, this one does the exact opposite. It spreads it all out. Let's start from the same place, an object at infinity. Those parallel rays come in, but this time, the concave lens kicks them outward, making them diverge. They never actually meet up on the other side. Instead, our eye traces them back to a focal point on the same side as the object. This creates a tiny, upright, virtual image. And this is what's so simple and beautiful about the concave lens. Remember how the convex lens had all those different outcomes? Well, the concave lens is incredibly consistent. As this shows, it doesn't matter where you put the object. The result is always the same, a smaller, upright, virtual image. It's a specialist. It only does one thing, but it does it predictably every single time. So we've seen both of these lenses do their thing. Now let's put them side by side in one final table to really lock in what makes them different. This table really lays it all out. Just look at the rows for the convex lens. It's the jack of all trades.
Depending on where you put the object, it can make an image that's real or virtual, bigger or smaller. Now look at the concave lens. It's the specialist. No matter what, you get a virtual, erect, and smaller image. You've got versatility versus consistency.
So really, if you remember one thing, it's this. Convex lenses converge light. They bring it together. Concave lenses diverge light. They spread it apart. One is a collector, the other is a distributor. And that single fundamental difference explains everything we've seen today. And there you have it. The science of bending light isn't just in a textbook. It's in the glasses on your face, the camera in your phone, and the telescopes peering into deep space. It all comes down to these fundamental rules. So the next time you see that bent straw, you'll know you're not seeing a trick. You're seeing physics. So what else can you spot around you that works just like this?